Okay, in this item, we've got a 2-bay single-story frame, has rigid connections, but the exterior columns are fixed, whereas the interior column is a pinned foundation. We're asked to describe the model that would be used in the flexibility method to analyze the system, but not to perform any actual calculations. So, first thing we want to do when we hear about flexibility method is to think about redundant reactions. So we've got R equal 3 components at the left, R equal 2 at the pinned, and R equal to 3 at the far right. For that fixed, that's a total of 8 reactions. We've got no hinges in here, so we've got 3 equilibrium conditions. So therefore, we have 5 in excess. We have 5 redundant reactions that we're working with here. Right, so we're going to relax all 5 of those. So this real system that had then the fixed pin fixed condition is going to then be thought of as a superposition of 6 different systems. Right, we have to select 5 redundant reactions to get rid of. So I'm going to get rid of all 3 on the right and all 2 in the middle, leaving us with a primary system that is a fixed end at the left. This may not be convenient from real calculation standpoints, but for a symbolic answer, it's not going to really matter. We just have to be consistent all the way through. Right, so we've got on this first one, then, to calculate what a bunch of displacements are in response to the actual load. So now, since we've removed 5, we really need to go back and identify what these are and to number and label these all up. So in no particular order, there's your first degree of freedom, there's your second degree of freedom or redundant reaction, there's your third and fourth and fifth in terms of displacements, and there's of course one force that goes with each and every one of those. So that means that we come over to here, we've got to calculate displacements that happen for each and every one of those relaxed reactions. Now those are going to be in the primary system, so that's delta 1 0, delta 2 0, delta 3 0, delta 4 0, and then delta 5 0. So we've got 5 of those that we're going to have to calculate. And thinking later on, then those will all go into a vector of those displacements that will be 5 by 1. Right? And then we're going to sequentially then replace each one of these by the redundant reactions. So I'm going to put a unit load of 1, and then we'll multiply this whole thing by the actual value of R1. And now we got to go calculate F11, F at 2 caused by 1, F31, F41, and F51. Right, so now this starts to get a little tedious, but it's not that bad. So now we're going to go put then the second redundant reaction in, and we're going to get those displacements. That would be F at 1 caused by 2, F2, 2, and let's see, F at 3 caused by 2, F4 caused by 2, and then F5 caused by 2. Right? Notice each and every one of these Fij's, that's the displacement at degree of freedom I due to the unit load at degree of freedom J, all other loads being 0. Right? We got to keep on going with this. We got a bunch more to do. There's one there, there's one there, and there's one there. Got to get all those, and then we got to get all the displacements in there. The displacement at 1 caused by 3 caused F at 2 caused by 3, the displacement at 3 caused by the unit load at 3, displacement at 4 by 3, displacement at 5 caused by 3. Right? We come on down here, and same thing, now we're at degree of freedom 4, so displacement at 1 caused by 4, displacement at 2 caused by 4, displacement at 3 caused by 4, displacement at 4 caused by 4, and displacement at 5 caused by 4, and then finally F15, F25, F35, F45, and then the rotation that goes with it, F55. Right? Now, that's the setup of the whole system, and that defines then all these displacements due to such and so scenario, all the same structure, the primary structure. We go back and we're going to write compatibility equations, because for each and every one of these relaxed reactions, we've now violated what was the case in the original one. That is, the displacement at a specific degree of freedom is going to be then the sum of what happens in these 6. So that would be displacement caused by the primary loads plus the sum of all of those from then 1 to 5 in this case. And let's see here, I think maybe I didn't multiply these like we needed to, right? This needs to be times R2, and this needs to be R3, this needs to be R4, that needs to be R5 to get those to add up, right? And this would be true for all 5, so we're going to have 5 equations. Remember, I started off collecting all these things down here in vectors. So here's that left-hand side. In this case, these would all be just zeros, values, right? That all 0 for all I, plus then each one of these, F1j times the respective R's. And so that's 5 by 1, and that will be 5 by 5. It will turn out, of course, that Fij will equal Fji by Maxwell's law of reciprocity, and that will give us, though, a pretty good summary of what this answer to, or analysis approach is by the flexibility method for this system. You could have chosen different redundant reactions, but you do have to relax 5 in order to make this all work out. And to do that by hand would be, of course, very lengthy.